Hello. So namaskar, adab, sat shri akal, kaisa hai, kem cho, hello and welcome in GATE Wallah. So student, in this class we are going to discuss vibration isolation. So till now in structural dynamics, I had covered three topics. In first class I had covered rotational vibration of single degree of freedom system. Then in second class I had discussed vibration of 2 degree of freedom. Okay. Now in force vibration case, one important concept comes, which is vibration isolation. So in this class I am going to discuss regarding vibration isolation. Okay, but I will not discuss the derivation because right at this time derivation is not important. Okay, and since right now in this class I am only focusing on vibration isolation, so I will not go into the detail of force vibration, in which we discuss derivation in the paid batch. So I will not discuss the derivation, but you will be able to solve all the problem related to vibration isolation. See, good evening, friend. So I'm going to cover vibration isolation. See, what is the meaning of vibration isolation? First understand. See, suppose what happens actually in force vibration case. Yes. Suppose in system, yes. Now system in system some unbalanced force is coming, and suppose it is F naught sine omega t. You can see this unbalanced force is periodic, and the amplitude of this unbalanced force which is coming in the system is F naught. So amplitude is F naught. Okay. So maximum value of this unbalanced force, you can see it is F naught. So if amplitude of unbalanced force is given, means in question F naught is given. What is omega? Can I say omega is the frequency of this equation in radian per second? And since it is the frequency of unbalanced force, this omega is also known as forcing frequency. Forcing frequency in radian per second. Okay. And generally it is equal to the speed of the system. So sometimes if question speed of the system is given na, so generally that is nothing but forcing frequency. Now what will happen? Ultimately what will happen na, since this unbalanced force is coming, so ultimately from this structure this force will transfer to the base. Okay. But what I want now in base, the force which is getting transferred, I want that it should be as low as possible. Okay, because if in base, suppose F naught is 300 Newton. Okay, so maximum value of this unbalanced force is 3 Newton, 100 Newton. And suppose this entire force is transmitting to the base, then it is good. Not it is not good for the structure. Na? It is not good for the base. Okay, because again in base against the reaction will come, and due to that this support can collapse. So what I want in vibration isolation, that the force which is getting transferred to the base, it should be less than F naught. That I want. That I want. Okay, less than F naught, because maximum value of this unbalanced force is F naught. Now suppose if this structure are rigid, suppose these all are rigid. Okay, then what will happen if they are rigid na? So this entire force will transmit to the base. So suppose the force which is getting transmit to the force base, I am denoting as Ft, and I will only write the maximum value of this force transmitted. Okay. So if this structure is rigid now, means right now I have not attached any isolation. So this entire force will transfer to the base. So force which is transferring to the base, okay, the maximum value of that force will also be equal to F naught in this case. Okay. But what I want, that the force which is getting transferred to the base, that is Ft, should be less than F naught. Okay. For that, what I will do now, I will try to isolate this part of the system from base. And for isolation, I generally use spring and damper, because right now we are studying vibration isolation. So instead of transferring this force through rigid structure, I am transferring through spring and damper. And this spring and damper in combined form, by using which I am transferring force to the base, this spring and damper in combined form is known as vibration isolation. Okay. It is known as vibration isolation. Now, the maximum value of unbalanced force is F naught sine omega t. Okay. But when it is transferring to spring and damper, now after that the force which is getting transferred to the base, the maximum value of that force I am denoting as Fd. And through this isolation, what I want, that Ft should be less than F naught. Okay, this isolation is only effective when actually Ft is less than F naught. But if suppose I attach this isolation, but suppose in some case I am getting Ft is more than F naught, okay, then it is not effective isolation case. Because why I am attaching this? To ensure isolation, and isolation means what I want. It is occurring or not, that I will discuss later. But what I want, that Ft should be less than F naught. This I want. Okay. Now whether at any instant Ft is less than F naught or not, because I want Ft should be less than F naught. For that we calculate a ratio which is known as transmissibility ratio. So calculate a ratio which is known as transmissibility ratio. Okay, I denote transmissibility ratio as epsilon. Okay. Now what is transmissibility ratio? It is the maximum value of force transmitted to the base, that is Ft, upon maximum value of this unbalanced force, which is F naught, and this ratio is transmissibility ratio. Okay. And if I want effective isolation, for effective isolation, can I say, if I want effective isolation, so for effective isolation, okay, this epsilon should be less than 1, that I want. Okay. Okay. And but suppose for some extent we are not getting epsilon less than 1, we are getting epsilon more than 1. How? That I will discuss after discussing the formula of epsilon. Okay. So for effective isolation, epsilon should be less than equal to 1. But suppose at some case, but if instead of epsilon less than 1, if you are getting epsilon more than 1, then can I say in that range that isolation is not effective? So in that speed range, I will not use that isolation. If I want isolation, this isolation as effective isolation, I need to use in that scenario when we are getting epsilon less than 1. So here one important thing which I need to discuss is, after finding the expression of epsilon, in which case we are getting epsilon less than 1, because in the case when we are getting epsilon less than 1, that is effective isolation case. If I am getting epsilon more than 1, that is not effective isolation. Okay. So if I want effective isolation, I will use the system in that speed range in which it is less than. But for that, I need to understand what is the formula to calculate epsilon. Okay. But that formula I am not going into to derive, because that is not important. Epsilon is Ft upon F naught. I am writing the formula. Just remember this formula. Now the formula to calculate this transmissibility ratio epsilon is square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Only you need to understand what is zeta and r here. Okay, so this ratio, transmissibility ratio epsilon, is nothing but square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay. Now here this zeta is nothing but it is damping factor. Okay. Zeta is damping factor, and we know the formula to calculate zeta. For general case means if spring is directly attached to a point mass and parallel to this spring if damper is attached. In that case, the formula to calculate damping factor is C upon 2 root over Km. Okay, or one more formula you can use, that is C upon 2m omega n, where C is nothing but the damping coefficient of the damper. As per this diagram, I am writing the formula. Yes. And K is the stiffness of the system, or you can say equivalent stiffness if more than one spring is attached. And M is the value of this point mass. M is the value of this point mass. Okay. Instead of that, you can use this formula also, C upon 2m omega n. Again, C is damping factor coefficient. M is mass of the value of that point mass M. And what is omega n? Omega n is natural undamped frequency. Natural undamped frequency. In short, you can also say natural frequency. Natural undamped frequency means if we will consider that in this system no unbalanced force is coming, neither damper is attached, then whatever frequency of this system will get, that is known as natural undamped frequency. And for general case, we already know the formula to calculate omega n is square root of Km. Square root of Km. But suppose if more than one spring is coming, then we'll use omega n equal to root over Ke by m. Okay. So when we are discussing free undamped vibration, we have discussed various cases of calculation of omega n. Okay. For this diagram, the formula to calculate omega n is root K by n. Yes. Now, what is R here? I'm writing here. You need to understand what is zeta, what is R. Okay. So R is nothing but it is omega by omega, and it is known as frequency ratio. R is nothing but frequency ratio, where omega is the value of this forcing frequency. Okay, forcing frequency, if equation of this unbalanced force is given, you will get omega. Or if speed of system is given, so you can remember that speed of system will always be equal to forcing frequency, which omega is given. Okay. Now, what is omega n? Omega n is again natural London frequency. So after calculating omega and omega n, you can calculate this frequency ratio R. Okay. So through this, you can calculate epsilon. If some numerical is coming, suppose omega is given, omega n is given, or you can calculate from this formula. Zeta is given, or otherwise you can calculate from this formula. If exam asking calculate transmissibility, now for numerical it is very easy. You can calculate epsilon, very easy. Yes. And if it is coming less than 1, it is effective isolation. If it is more than 1, means that isolation is not effective at that position. Okay. But now, sometime question can come that in which range this isolation will be effective, in which range this isolation is not effective. Okay, that we will not conclude through numerical. Before going to numerical, we need to know when it is effective and when it is not effective. When it will be effective, when epsilon we are getting less than 1. When it is not effective, when epsilon is more than 1. Okay. So for that, what we do now, through this equation, we plot the graph between epsilon. In y-axis, I am taking epsilon, that is transmissibility ratio, and frequency ratio, that is R, for any fixed value of zeta. Because once you have designed this isolation, means K is fixed, C is fixed, M is fixed. So you will get fixed value of zeta, because zeta is C upon 2 root over Km. Similarly, we will get fixed value of omega n also. But right now, omega is in our hand. If I will take that speed of the system in which frequency ratio is, if omega is changing, R will also change. We will take that value of frequency ratio or omega in which we are getting epsilon less than 1. Okay. And if in the range, in that value of omega in which epsilon is coming more than 1, we will try to ensure that actual frequency ratio is not equal to that. Because if epsilon is more than 1, that is not effective isolation. So what we are doing now, we are plotting the graph between epsilon and R for any fixed value of zeta. Like you can draw for zeta equal to 0, means it is undamped, means no damper is there. Zeta equal to 0.1, zeta equal to 0.2, zeta equal to 0.3. Okay. So for any fixed value of zeta, I am drawing the graph between epsilon and R. And whatever graph I am drawing now, I am drawing from that equation. You need to understand the pattern of that graph. So right now, try to understand. At last now, whatever image of final graph is coming now, just click the picture of that image in your mind. Because now, image will never eliminate from your mind. So whatever final picture is coming, just remember that. Okay. See. First of all, now you can check whatever is the fixed value of zeta. Whatever is the fixed value of zeta, you can check. If R equal to 0 and root 2, okay, 0 is not a point because 0 means it is in rest. But since we are drawing the graph, that's why I am taking one value R equal to 0 also. But here important is R equal to root 2 because that is practical value. But whatever is the value of zeta, you can see for R equal to 0 and root 2, now this epsilon is always equal to 1. How, sir? How? You can see, check from you this through mathematics. See, in above and below term, you can see only difference is coming in this term. It is 1 plus 2 zeta R whole square. It is this plus 2 zeta R whole square. So this part is same. Now try to understand if this part is equal to 1. In that case, can I say above and below term will be same? And if above and below term is same, means transmissibility ratio will be 1. What you are asking, Tanushree, what I have to repeat? See, through this spring and damper, we are transferring force to the base. The force, maximum value of force transmitted to the base is Ft, and the ratio of Ft and epsilon, F naught is known as epsilon. But why I am attaching this epsilon? Because isolation, because I want Ft should be less than F naught. So for the range in which actually epsilon is coming less than 1, means Ft is less than F naught, that isolation is known as effective isolation. But in the range is in which instead of getting epsilon less than 1, if we are getting epsilon more than 1, that is known as not effective isolation case. So I want this, I don't want this. Okay. Now for that we should know the formula to calculate epsilon. This is the formula to calculate epsilon, that is transmissibility ratio. That formula you have to remember. The formula is square root of 1 plus 2 zeta R whole square upon square root of 1 minus R square whole square plus 2 zeta R whole square. Where zeta is nothing but damping factor if it is given good. Otherwise formula to calculate zeta is C upon 2 root over Km. It is for general case, na? C is the damping coefficient of the damper, M is the mass, and K is the stiffness. Instead of that, one more formula is there to calculate zeta. It is C upon 2m omega n. Both formula are same. Okay. What is omega n? Omega n is the natural undamped frequency of the system. Means in this system, if no unbalanced force is there, no damper is there, then whatever frequency will get, that is known as natural undamped frequency. And for general case, formula to calculate omega n is square root of K by M. Okay, K by M. Now, what is R here? It is frequency ratio, which is nothing but forcing frequency upon natural undamped frequency, that is omega by omega. Now, for numerical, it is very easy. If zeta is given, otherwise C, K, M will be given, calculate zeta. Omega n is given, calculate R. Put here, you will get epsilon. If epsilon is coming less than 1, it is effective. If it is more than 1, means it is not effective. But okay, but it will come in numerical. Okay. But before proceeding to the numerical, I need to find in which range of R for any fixed value of zeta it is less than 1, and for which value of R it is more than 1. That is important discussion, because when it is less than 1, that isolation is effective, but when it is more than 1, that is not effective. So I should know now in which range it is less than 1, in which range it is more than 1. For that, through this mathematical equation, what I am doing, I am drawing the graph between epsilon and R. In y-axis, I am taking epsilon, transmissibility ratio. In x-axis, I am taking R, that is frequency ratio, and I am drawing this graph for any fixed value of zeta. Okay. But you can conclude one thing, whatever is the value of fixed value of zeta, whether zeta is 0, zeta is 0.1, zeta is 0.2, zeta is 0.3, for R equal to 0 and R equal to root 2, epsilon will always be equal to 1. I will write everything, don't worry, just try to write down, just try to understand the concept. Okay, see. Why, sir? I am writing this formula in fresh page. Epsilon is equal to x square root of 1 plus 2 zeta R whole square upon square root of 1 minus R square whole square plus 2 zeta R whole square. Now you can see in above and below term, you can see now only difference is coming in this term. Here this term is 1, this term is 1 minus R square whole square. This part is same. So see here this term is 1. So can I say when this term is also 1, in that case above and below term will be same. And if above and below term is same now, then epsilon will be equal to 1. Okay. Now when this will be equal to 1 now, first of all when R equal to 0 and second R equal to root 2, you can check. Here if we put R equal to 0, this part is 0. So it will be 1 square equal to 1. And if it is coming 1, above and below part is same. So epsilon will come equal to 1. I am just writing this, but you need not to write. At last I will make the summary. So for R equal to 0, epsilon equal to 1. Second, above and below term will be same when R is equal to root 2. Because if we put R equal to root 2 square is 2. 1 minus 2 is minus 1. But square of minus will be plus now, so it will be 1 square. And 1 square is nothing but 1, because the square of minus is plus. So if you are putting R equal to root 2, in that case also it is coming equal to 1. And if it is this term is coming equal to 1, means again above and below term is same. So again epsilon will come equal to 1. Means whatever is the value of zeta now, for R equal to 0 and for R equal to root 2, epsilon will always be equal to 1. Okay, suppose this is the point which is representing R equal to root 2. This is the point which is representing R equal to 0. So I know whatever is the value of zeta for R equal to 0 and for R equal to root 2, epsilon is always equal to 1. Similarly, you can check if R is less than root 2 now, you can check epsilon will always be greater than 1. Whatever is the value of epsilon now, but it will be greater than 1. Similarly, if R is greater than root 2, epsilon will be equal to less than 1. How I am explaining? Okay, see, if R is less than root 2 means take any value. When I am saying less than root 2 now, means between 0 to root 2, I am not including 0. So between 0 to root 2, take any value. Suppose I am taking 1. So whatever this term will come now, it will be less than 1. Or see, if it is less than 1, it is 1, and it is coming, if it is coming less than 1, means can I say above term will be more and below term will be less? And if above term is more, epsilon will be greater than 1. Okay, and why it is less than 1? See, just put R equal to 1. It will be R equal to 1 square 1, 1 minus 1 0, 0 square is 0. So whatever this value is coming, it is coming less than 1. You can put any value of R which is less than R root 2, and if you are putting R which is less than root 2, now whatever this value will come, at that will be less than 1, because at root 2 pattern is changing. Means between 0 to root 2 it is less than 1, at root 2 it is exactly equal to 1, and for R greater than root 2 it will be more than 1. So since when R is less than root 2 means it is between 0 to R root 2, it is less than 1, and if it is less than 1, this above part will be more, below part will be less, because it is 1, it is suppose 0.8 is coming, so it is less now, but less than 1, and if above part is more, epsilon will come greater than 1. Similarly, if r is greater than root 2 na, whatever value of this stuff will come, it will come more than 1. Like take any value which is greater than root 2. Okay, suppose I am taking 2, 2 is greater than root 2 na, root 2 is 1.414, so r is 2 is greater than root 2 na. So if I am taking r equal to 2, it will be 2 square, 2 to the 4, 1 minus 4, it will be minus 3. Now minus 3 whole square, square of minus is plus, so it will be 3 square, and 3 square is 9. So whatever this value is coming now, but you can see 9 is more than 1. So in that case, below part will be more and above part will be less. And if above is less, below is more, means whatever this ratio will come, it will be less than 1. This you can remember. Whatever is the fixed value of zeta, at r equal to 0 and root 2, epsilon will be equal to 1. Between 0 to root 2, epsilon is greater than 1, means isolation is not effective. When it is effective? When r is greater than root 2, epsilon is less than. This is very important conclusion, okay? But that I will show in the graph, don't worry, okay? But another pattern, okay, that I know whatever is the graph, between this range it will be more than 1 epsilon, after this epsilon will be less than 1. But how we can plot this graph? So I am drawing one by one. Suppose firstly I am drawing this graph, you need to only understand the pattern. Suppose first I am drawing for zeta equal to 0. If we draw this graph for zeta equal to 0, it will be, if zeta is equal to 0 means no damper is there. This part will be 0, so it is 1 upon. For zeta equal to 0, this part will be 0, so it will be square root of 1 minus r square whole square. Okay. Now you can calculate the value. But see, if you are solving the numerical and mainly for zeta equal to 0 you are calculating, and suppose in question epsilon is given, your objective is to calculate r. Don't be in a hurry. You don't say, sir, 1 minus r square whole square, then if you are calculating a square root, it will be 1 upon 1 minus r square. If you are calculating a square root, the square root of this is 1 minus r square. Don't be in a hurry. See, what I am trying to say now, 1 minus r square can be positive also, can be negative also. Suppose if it is positive, positive means plus 2. So it will be plus 2 square, and the square root of plus 2 square will be plus 2, because square root is always positive. So in that case, can I say when it is positive, a square root of this will be equal to this value? It is correct. But suppose at an instant, if we are getting 1 minus r square negative, negative means suppose minus 2, you can get na, if this value is more, it will be negative, yes. So if it is coming minus 2, so it will be minus 2 whole square, but don't be in a hurry. See, square of minus is plus, 1 minus r square is negative, but square of minus will be plus, so it will be plus 2 square, and square root of plus 2 square is again positive 2. So can I say if it is coming negative, then square root of this will be minus in bracket 1 minus r square, because minus of minus 2 is plus 2. So what I am trying to say, if you are solving the numerical, and mainly if epsilon is given and your objective is to calculate r na, if you bring this outside root, just ensure in this side I will write plus and minus, and calculate the value of r by taking plus sign also, calculate the value of r by taking minus sign also, and whichever practical values come, practical means r should always be positive real number, because frequency ratio will be positive and it should be real number, okay? That is practical value of r. But if this equation for numerical, I am saying if epsilon is given, you are calculating r. If you are bringing this outside root, keep this plus or minus, okay? Yeah. But that is different thing. Right now this is the equation. Now you can see, again if we put r equal to 0, epsilon will be 1. R equal to root 2, epsilon will be 1. R is less than root 2, epsilon is greater than 1. That I already calculated, concluded. If r is greater than root 2, epsilon will be less than 1. But what will be the pattern of this graph? So you can see initially now, when I will increase, just you need to understand the pattern, okay? Because we will not go too much in mathematics. Initially, if we are increasing the r from 0 to 1, what I am saying, if we are increasing the r from 0 to 1, what will happen if we are increasing the r from 0 to 1 na, this epsilon will increase. How? If we are putting r equal to 0, you can see at r equal to 0, epsilon is coming equal to 1, okay? Now similarly, if we put r equal to 1 na, this epsilon will come infinite. You can check r equal to 1, 1 minus 1 is 0, 1 by 0 is infinite. So definitely between 0 to 1, it will increasing from 1 to infinite. Now epsilon cannot be more than infinite. So after r equal to 1, if you increase the r na, epsilon will decrease, okay? But that is not much discussion point. Just what I am trying to say, for zeta equal to 0, if you are drawing the graph na, suppose this is r equal to 1, okay? So from r equal to 0 to 1, epsilon is increasing. This is the graph for zeta equal to 0, and after that epsilon is decreasing, okay? Okay, but it is not important. Here we are getting epsilon infinite. No, because I want epsilon 1 less than 1. So important thing is between 0 to root 2 epsilon is more than 1, whatever is the graph, and after r greater than root 2 epsilon is less than 1. Just ensure this in your graph, that between 0 to root 2 it is more than 1, and after r is greater than root 2 it is less than 1. Okay, but sometime examiner can ask this graph for zeta equal to 0 na. That's why I draw exactly equal zeta equal to 0. It is r equal to 1. Okay. Now try to understand the pattern. As will increase zeta, right now it is for zeta equal to 0. Now suppose next fixed value of zeta I am taking equal to 0.1. Now I need not to write equation, just understand the pattern. Now when you will draw graph for zeta equal to 0.1 also, na, in that case also between 0 to root 2 epsilon will be more than 1. At root 2 epsilon will be equal to 1. And at greater than r greater than root 2 epsilon will be less than 1. But what is the pattern now? Between 0 to root 2, that you need to understand, remember. Between 0 to root 2, if we are increasing the zeta na, the value of epsilon will decrease. Okay. This mathematical equation is such that between 0 to root 2, if we will increase the zeta na, between r equal to 0 to root 2, if we will increase the zeta, epsilon will decrease. But it is decreasing, but it will remain more than 1. Because between 0 to root 2, epsilon is more than 1. Okay. At r equal to root 2, there will be no change. Means at r equal to root 2, epsilon will be equal to 1. And at r is greater than root 2, na, by increasing the zeta, epsilon will increase. Try to understand the pattern. What I am saying? Between 0 to root 2, by increasing zeta, epsilon will reduce. But when r is greater than root 2, in that case, by increasing zeta, epsilon will increase. Okay, so here epsilon is decreasing, but here epsilon is increasing. But here epsilon is decreasing, but it will remain more than 1. And here epsilon is increasing, but it will remain less than 1. Okay, so this is the pattern. Means after r equal to root 2, na, pattern is changing. This is the graph for zeta equal to 0. And suppose this white graph is zeta equal to 0.1. Okay, if you remember the image of this graph, now you will never do any mistake. Okay, similarly, suppose I am drawing the graph for zeta equal to 0.2. Again, we are increasing the zeta. So between this range, epsilon will increase, but it will remain less than 1. After this range, epsilon will increase, but it will remain less than 1. So graph will be like this. Means between this range, graph is going below. After this, graph is going above. But here it will remain more than 1. Here it will remain less than 1. Okay. So it is for suppose zeta equal to 0.2. So this is the graph of transmissibility and r. Okay. And when it is effective, when r is greater than root 2. So this is the pattern. I am making a final summary. Sometimes question can come from this graph. Now, if you remember the image of this graph, this conclusion you can easily understand. Okay, first conclusion is whatever is the fixed value of zeta na, you can directly remember for r equal to 0 and root 2 epsilon equal to 1. Similarly, b for r less than root 2. When I am saying r less than root 2 means it is between 0 to root 2. Epsilon is more than 1. It is more than 1 means isolation is not effective. And when r is greater than root 2, epsilon will always be less than 1 means it is effective. So whenever we are doing designing na, we'll try to take that speed of the system na, in which value of r is coming greater than root 2. It is far away from this, because only in that case epsilon will be less than 1. That is, it will be effective isolation. Otherwise, if r is less than root 2, this isolation is not effective. Okay. Second, regarding graph, what I'm trying to say. Okay, see. Second, between r equal to 0 to root 2, it means in not effective isolation case, because in this range isolation is not effective. In this range, if we'll increase the zeta means damping factor, can I say epsilon will decrease? Yes. But although epsilon is decreasing, but it will remain more than 1 means not effective isolation. Okay. So sometimes question can examiner can ask if r is less than root 2. In that range, or it is not effective isolation case, by increasing zeta, what will happen? Epsilon will increase or decrease, or it will remain same, so it will decrease. Okay. Similarly, can I say if r is greater than root 2, instead of that, examiner can also say in effective isolation range, because when r is greater than root 2, it is effective isolation range. In that range, by increasing the zeta, epsilon will increase. That's why now, with respect to isolation point of view, now less zeta is good. Because now we'll try to keep our design in this range, and in this range by increasing zeta, epsilon is increasing. and I want less value of epsilon. It is increasing, but it will remain less than 1. Okay. And definitely at r equal to root 2, there will be no change now, because epsilon is always equal to 1. So just this is the conclusion which I had drawn from this graph. So if we keep the image of this graph, you can see between 0 to root 2, it is always worse than 1, more than 1, sorry, greater than r root 2, epsilon is always less than 1. In this range, by increasing zeta, epsilon is decreasing, but it is remaining more than 1. If r is greater than root 2, by increasing zeta, epsilon is increasing, but it will remain less than 1. Okay. Okay. But suppose sometime question can come, examiner will say the range of r is not given, and examiner will say by increasing zeta, epsilon will increase or decrease, or it will remain same. So I cannot say. I need to tell what is the range of r. If it is in not effective isolation range, means in this range, in that case by increasing zeta, epsilon will decrease. If it is effective isolation case, in that case by increasing zeta, epsilon will increase. And if r is exactly equal to root 2, there will be no change in epsilon by increasing the zeta. Okay, so just remember this graph, you will never do any mistake. Now I am discussing these things with some numerical. It will be better clear. Like, see this question. For numerical, this is the final formula. Na? Yes. In the single degree of freedom under damped spring mass system shown in figure, an additional damper is added parallel to the system, but system will remain under damped. That means if we are attaching one more damper, na, zeta will increase, but it will remain less than 1. What is under damped system? Okay, you will study in damped vibration. When zeta is less than 1, that is under damped. If it is equal to 1, critical damped. It is more than 1, over damped. So right now it is under damped. Okay. Then which of the following statement is always true? Always true means it is always true. A and B saying, A is saying transmissibility will increase, B is saying it will decrease. C is saying time period of free oscillation will decrease, D is saying time period of free oscillation will increase. So see, firstly, okay, this option C and D is regarding damped vibration, that I have not discussed, but I will write the formula. Okay, mainly I was going to discuss A and B. See, first of all, what about epsilon? So here range of r is not given because forcing frequency is not given. I don't know whether r is less than root 2 or greater than root 2. If r is less than root 2, what will happen? It will attach one additional damper. So what will happen now? The damping coefficient in parallel case now, equivalent damping coefficient will be addition of these two. So can I say by attaching additional damper, C will increase, and C is increasing, zeta will increase. Okay. Now by increase in zeta, what will be the effect on transmissibility? For that I should know whether r is less than root 2 or greater than root 2. If it is less than root 2, by increasing zeta, epsilon will decrease, means this will be correct. If it is more than root 2, by increasing zeta, epsilon will increase, means this will be correct. But right now range of r is not given. So miss, can I say that is not always true, option A and B? So they are not correct, because they will be correct if range of r is given. Okay. Yes. Now what about time period of free vibration? Free vibration means it is free damped vibration because damper is attached. Na? So see, this will study in damped vibration, but you can remember the formula to calculate frequency of free damped vibration. Free damped vibration means I am not considering any external force, but I am considering damper. Examiner has written free vibration. Na? In free vibration, damper word is not written here, but damper is shown in the diagram, means it is free damped vibration. And for free damped vibration, formula to calculate frequency is omega d, and formula to calculate this is omega, and omega n is natural undamped frequency, means there is no damper. Omega n is always root k by n, root over 1 minus zeta square. So what will be time period? Time period is 2 pi by omega, so 2 pi by omega d. So it will be 2 pi by omega d is omega and root over 1 minus zeta square. Okay. Right now see, zeta is changing. Okay. So what will happen? Zeta is changing, but it is less than 1. This equation is only valid for, this is the equation for under damped system when zeta is less than 1. So it is already mentioned the question. Zeta is less than 1. Now you can see, if zeta is less than 1, by increasing the zeta now, this 1 minus zeta square part will reduce. Okay. Because if zeta is less than 1, zeta square will also be less than 1. So as you will increase zeta now, this term will increase. Suppose at any value of zeta it is 0.2. So 1 minus 0.2 is 0.8. Now if we will increase the zeta, this part will increase. So from 0.2 it has increased to 0.4. So it will be 1 minus 0.4, which is 0.6. So what I am trying to say, if zeta is increasing, this 1 minus zeta square part is decreasing. And if this part is decreasing, omega d will decrease. And if omega d is decreasing, can I say time period, because it is the reciprocal omega d, it will increase. So by increasing zeta, time period is increasing. Time period is increasing. So out of C and D, D is correct, C is not correct. Okay, but important conclusion in transmissibility, neither A is correct nor B is correct because range of R is not. Okay. Yes, this is simple numerical. What this question is saying, okay, you can see a machine of 250 kg mass is supported by a spring of total stiffness 100 kilonewton per meter. Machine has a unbalanced rotating force of 350 newton. Means just remember, imagine it is the amplitude of the force at a speed, this in this speed. So this will be forcing frequency, but it is given in rpm. Convert that in radian per second. Assume damping factor 0.15, value of zeta is given. So exam asking transmissibility ratio. Here our objective is to calculate transmissibility ratio. The mass of the system m is 250 kg. Just write the value of given data. Supported by the spring whose stiffness is k 100 kilonewton per meter. Always use SI unit, na? So in newton per meter, 1 kilonewton is 1000 newton. So it will be 100,000 newton per meter. So if k is m is given, we can calculate omega. Okay. Now the unbalanced force, amplitude of unbalanced force is 350 newton. Okay. The speed is 360 rpm. Sorry, 3600 rpm. So it is also forcing frequency. Okay, but convert that in radian per second. And whatever speed of the system is coming in radian per second, that is producing frequency radian per second, which I am denoting as omega. So it will be, if speed in rpm is given, what is the formula to calculate speed in radian per second? It will be 2 pi into speed in rpm, which is capital N, divided by 60. So from this we'll get the value of forcing frequency in radian per second. It will be 2 pi, N is 3600 divided by 60. How much it is coming? 2 pi 3600 divided by 60. You can check. It is coming 376.991 radian per second. Good. Assume damping factor 0.15. So directly the value of zeta is given. It is 0.15. Then we have to calculate the value of transmissibility ratio epsilon. Okay. Now what is the formula to calculate epsilon? That I have already discussed. It is the square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r whole square. So from this to calculate epsilon, now I need to calculate two values. One is zeta, second is r. So zeta is already given, it is 0.15. So now I need to calculate r. R is omega by omega n. Omega is forcing frequency, omega n is natural London frequency. So omega is already given. Now omega n is square root of k by m. K is the stiffness of the system or equivalent stiffness, which is 100,000 newton per meter. M is mass, which is 250 kg. So how much omega n is coming? Root over k 100,000 divided by mass 250. Is it coming 20 radian per second? And after calculating omega n, now we can calculate frequency ratio r. It is omega by omega n. Yes, omega is 376.991 divided by 20. So how much the value of r is coming? It is coming 376.911 divided by 20. It is coming 18.8496. Okay, you can check calculation. Now you can see whatever is the value of this r, now this is greater than root 2. So it is 100% sure if I will put this value in this equation, whatever epsilon will come, now it will be less than 1. Reason? Because r is greater than root 2, and for r is greater than root 2, epsilon will always be less than 1. But this you will automatically get if you are solving the numerical. So numerical you will get automatically that value. Na? Okay. It is square root of 1 plus 2 zeta r. Zeta is 0.15. Yes, into r is 18.8496 whole square upon square root of 1 minus r square. R is 18.8496 square, then whole square, plus 2 zeta. Zeta is 0.15 r, 18.8496. No, calculation is your partner. How much it will come? This is 2 into 0.15 into 18.8496, 2 zeta, then square root, plus 1, then root of this. This above part is coming 5.7426, then below part is 1 minus 18.8496 square, then again whole square, plus 2 into 0.15 into 18.849 square, then root of this. Calculation is your partner. It is coming 354.3525. So how much this ratio will come? 5.7426 divided by 354.3525. Is it coming 0.0162? You can see whatever this value is coming, it is less than 1. Okay. So for this question, the value of transmissibility ratio is 0.0162. Okay. Matching with which option? Option C. So for this question, the correct answer is C. Clear? Yes. Now this is very good question. You can, if you want, you can star mark this question. If you understood the graph between epsilon and r na, okay, means this graph. This graph means between 0 to root 2, epsilon is always greater than 1. For r is greater than root 2, epsilon is always less than 1. Now between 0 to root 2, if you increase the zeta, epsilon will decrease, but it will remain more than 1. If r is greater than root 2, by increasing zeta, epsilon will increase, but it will remain less than 1. Okay. Then you can easily solve this numerical, this question. This is very good question. What this question is saying, a machine, I'm first rating this question, a machine of mass 100 kg, so M is 100 kg, is subjected to external harmonic force with frequency 40 radian per second. See, it is the frequency of force, and frequency of force means it is forcing frequency, and it is given in radian per second, means omega is given, because omega is nothing but forcing frequency in radian per second. So omega is given. Now designer decide to mount the machine on the isolator to reduce the force transmitted. Now isolator can be considered the combination of stiffness and damping factor zeta. Okay, so it is the combination of K and zeta. Now we have 4 isolator in which different value of K and zeta is given. Like for one, K is 640 kilonewton per meter, zeta is 0.7. Here also K is 640 kilonewton per meter, but zeta is 0.07. So here zeta is more, here zeta is less. Here K is 22.5 kilonewton per meter, zeta is 0.7. Here K is again 22.5 kilonewton per meter and zeta is 0.07. Okay. Now, if value of K is changing, means omega n will change. Omega n will change means R will change, because R is omega by omega n. Okay. Second, zeta is changing. So you can see now ultimately 2 different value of K is given and 2 different value of zeta is given. So total we are getting 4 combination. This with this case zeta 0.7, with this case zeta 0.07. Now with another value of K again zeta 0.7, with another value of K again zeta 0.007. Now you have to tell, we have to arrange this isolator in ascending. Ascending means increasing order of force transmitted to the base. Means if Ft is more, Ft is lesser, that will come first. If Ft is more, that will come later, because we have to write this sequence in the increasing order of Ft. And increasing order of Ft means, can I say it will be increasing order of transmissibility ratio epsilon. Okay. Means for the case in which epsilon is coming lesser, we have to write first. For the case which epsilon is coming more, we have to write later. Now you can solve this problem in 2 approach. One is now for all the cases by using K, calculate omega and then calculate R by using omega by omega, and zeta is already given. Now if you have calculated R and zeta, you have formula to calculate epsilon, just a numerical. So put that value of zeta and R in the equation of epsilon. Ultimately you will get the epsilon for all the cases, for case 1 also, case 2 also, case 3 also, case 4 also. It will take time, but this approach, if you don't know the graph, you can use this approach. Okay. And then after calculating numerical value, you can see for which value epsilon is coming lesser, write first, and if epsilon is increasing, according to that write the sequence. But second, this question you can easily predict for which case R will be lesser, for which case epsilon will be lesser, for which case epsilon will be more, through graph. For that, what I am doing now, we are getting 4 cases, 1, 2, 3 and 4. For all the cases, now calculate R and zeta. So see, for first case K is 640 000. Okay, what I am doing, ultimately 2 value of K is given na. So first I am calculating for K equal to 640 kilonewton per meter. What will be the value of R? Frequency ratio. See, when K is 640 kilonewton per meter, in Newton per meter it will be 640 000 Newton per meter. So now calculate omega, and omega n is root over K by M. So see, K is 640 000 Newton per meter divided by M. M is mass, which is 100 kg. So how much omega n is coming? It is coming square root of 640 000 divided by 100. It is 80 radian per second. Okay. Now what will be the value of frequency ratio R? It is omega by omega n. Omega is 40, omega n is 80. So it will be 0.5. Now whatever this value of 0.5, but you can see it is less than root 2. And if r is less than root 2, na, epsilon will always be greater than 1. If r is less than root 2, epsilon will always be greater than 1. Okay, but that I will discuss. Okay, so you can see two value of r is given. When k is 640, r is 0.5. This is the first value. But in this case, for this value of r, we have to discuss two cases, when zeta is 0.7, when zeta is 0.07. But one more value is given, k is also 2 in case 3 and case 4, k is also 22.5 kilonewton per meter. So now for k equal to 22.5 kilonewton per meter. In Newton per meter, it will be 22500 Newton per meter. What will be the value of omega n? It is square root of k by m. For this case, k is 22500, m is 100 kg. So how much omega n is coming? Root over 22500 divided by 100. It is coming 15 radian per second. So what will be frequency ratio r? It is omega by omega n. Omega is 40, omega n is 15. How much it is coming? 40 divided by 15, you can say it is coming 2.667. Now whatever is this value of r, now you can see it is more than root 2. Okay, it is more than root 2. Why more than root 2? Root 2 is 1.414, na? So it is more than root 2. And if it is more than root 2, na, epsilon will be less than 1. But for this value of r, we have to discuss two cases. For case 3, case 4, r will be this value. But in case 3, zeta is 0.7. In case 3, zeta is 0.07. So ultimately, we are getting 4 combination. Now, for combination 1, now I am directly writing the value of r and zeta. Na? So see, r is 0.5, which is less than root 2, and zeta is 0.7. For isolator 2, again r is 0.5, but now we are decreasing the zeta. Zeta is 0.07. Now, for isolator 3, the value of r is 2.667, which is more than root 2. And zeta is 0.7. Yes. And for isolator 4, again r is 2.667, which is more than root 2, and zeta is 0.07. Now, one approach is we have calculated r and zeta for all the cases. Now, input the value in the expression of epsilon, calculate epsilon for all the case. After that, write in the increasing order of epsilon, because that is asking. But this conclusion you can make from graph also. How? We know if we are plotting the graph between epsilon and r, we know between r equal to 0 to root 2, it is r equal to root 2, epsilon will always be greater than 1, and for r greater than root 2, epsilon will be less than 1. Second conclusion, between 0 to root 2 range, if you increase zeta, epsilon will decrease, and for r greater than root 2 range, if you increase zeta, epsilon will also increase. Okay, so first I am drawing this graph for lesser value of zeta. See, for lesser value of zeta is 0.07. So if I will draw the graph for zeta equal to 0.07 na, can I say graph will be like this? Suppose this is the graph. Only I have ensured one thing, when r is less than root 2, r is epsilon is greater than 1. If r is greater than root 2, epsilon is less than 1. So suppose this is the graph for zeta equal to 0.07. Now we are increasing the zeta. So next increased value of zeta is 0.7. So if we increase the zeta na, between r equal to 0 to root 2 range, epsilon decreases. But it is decreasing, but it will remain more than 1. And for r greater than root 2 range, epsilon will increase. It is increasing, but it will remain less than 1. So this is the graph for zeta equal to 0.7. Now just mark the value of epsilon for these 4 cases. For case 1, r equal to 0.5 and zeta is 0.7. First of all, suppose r equal to 0.5 is less than root 2, so it will come somewhere here. Suppose here r is equal to 0.5. So draw a vertical line from this point. Now for case 1, r is equal to 0.5 and zeta is 0.7. This is white graph is the graph for zeta equal to 0.7. So you'll get this value of epsilon. So can I say this is nothing but epsilon 1? Yes. Now for case 2, r is equal to 0.5 and zeta equal to 0.07. So this is the line of r equal to 0.5 and zeta is 0.07. So this is the graph for zeta equal to 0.07. So I will get epsilon here. So this is the value of epsilon 2. So you can see out of epsilon 1 into epsilon 1 is lesser, 2 is more. Yes. Now case 3, r equal to 2.667. Now r equal to 2.667 means it is greater than root 2. So this value of r will come somewhere here. Here r is 2.667, whatever this value, but it is more than root 2. Now in case 3, R is equal to 2.667 and zeta equal to 0.7. So this white graph is the graph of zeta equal to 0.7 and R equal to 2.667. So from this draw a vertical line. So it is intersecting the graph of zeta equal to 0.7 here. So can I say this is the value of epsilon for case 3, that is epsilon 3. Now for case 4, again R equal to 2.667, which will draw a vertical line corresponds to this point. Now zeta equal to 0.07. So this is the graph for zeta equal to 0.07. So this line is intersecting the graph of zeta equal to 0.07 at this location. This is the graph of zeta equal to 0.07. Na? So this is the value of epsilon 4. So what is the increasing order of epsilon? So first of all, minimum value of epsilon is coming for case 4. Then case 3, it is, yes. Then epsilon 1 is more and epsilon 2 is maximum. So can I say here increasing order of epsilon is 4, 3, 1, 2. Okay, 4, 3, 1, 2. 4, 3, 1, 2. Matching with which option? Option C. Means for isolator 4, epsilon is minimum. And this is the increasing order of epsilon. Means for isolator 2, epsilon is maximum. So for this question, the correct answer is option C. This is very, very good question. Clear? Yes, I am discussing some more numerical also. See what this question is saying. A machine of 200 kg mass. So mass is given, it is 200 kg. Suspended on the spring or total stiffness 80 kilonewton per meter. In Newton per meter, it will be 80,000 Newton per meter. Machine has unbalanced rotating force of amplitude 300 Newton. So amplitude of unbalanced force is given. It is 300 Newton. At speed 3600 RPM. So the whatever is the speed of system is given, that is forcing frequency, but it is given in RPM. Convert that in radian per second. And forcing frequency in radian per second we denote as omega. So we speed in RPM is capital N. Definitely speed in radian per second will be 2 pi capital N by 60. So 2 pi capital N is 3600 divided by 60. So how much omega is given? Coming 2 pi 3600 divided by 60. 376.991. Okay. Now the damping coefficient of the damper means value of C is given. It is 1600 Newton second per meter. Damping coefficient is this, na? So you have to calculate value of transmissibility ratio. Round up to 2 decimal place. Okay. So if exam asking final value round up to 2 decimal place. So at least do calculation up to 3 to 4 decimal place. So your answer will be correct up to 2 decimal place, na? Yes. Now to calculate epsilon, I need to calculate two things. One is zeta, second one is R. What is R? R is omega by omega n. So omega is already known. It is radian per second. Now for R, I need to calculate omega n, that is natural undamped frequency. Now stiffness of the system and mass is given. So we know the formula to calculate omega n is square root of K by M. Now K is 80,000 Newton per meter divided by mass M is 200. So how much omega n is coming? Root over 80,000 divided by 220 radian per second. So now I can calculate R. R is nothing but omega by omega n. Omega is 376.991. Omega n is 20. So how much it is coming? 376.991 divided by 20. That is 18.8496 or 95. Okay, and whatever this value, it is more than root 2. So I am 100% sure since R is more than root 2 now, whatever value of epsilon will come, it will be less than 1. Okay. So this is R. Now next I need to calculate zeta. Zeta is damping factor. Now the formula to calculate zeta is C upon 2 root over Km or C upon 2m omega n. 2m omega n. So C is 1600 upon 2 root over K. K is the equivalent stiffness or stiffness of the system 80,000 Newton per meter. M is mass, which is 200 kg. So we can calculate zeta, how much it is coming? 1600 divided by 2. Answer divided by root over K 80,000 into 200. Is it coming? 0.2. So now after calculating the value of R and zeta, now we can calculate transmissibility ratio epsilon. Okay. Now see, we know the formula to calculate epsilon. It is square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Just put the value of r and zeta, you will get epsilon. Now this is calculation, na? Square root of 1 plus 2 zeta, zeta is 0.2, r is 18.8496 whole square upon the square root of 1 minus r square, r is 18.8496 square, then whole square of this, na, plus 2 zeta r whole square. So 2 zeta, zeta is 0.2 into 18.8496 whole square. Now calculation is your part, that I am not going to discuss. So how much epsilon will come? First I am calculating above part. It is 2 into 0.2, 18.8496, then square of this, sorry, plus 1, then square root. This above part is coming 7.6059. Below part, okay, this is 1 minus 18.8496 square, then square of this plus 2 into 0.2 into 18.8496, then square of this, then square root of whole term. It is coming 354.3876. So how much epsilon is coming? 7.6059 divided by 354.3876. Is it coming 0.0215? You can check the calculation, na? So for this question, the value of transmissibility ratio epsilon is coming 0.0215. 0.0215. Now examiner asking final answer round up to 2 decimal place. So mathematically, if you round up this value up to 2 decimal place, it will be 0.02. So in fill in the blanks, we'll put 0.02. Clear? So this is correct answer for this question. Okay? Yes. Next, this question. So I am going to discuss this question. What this question is saying: a refrigerator unit has a mass of 35 kg. So mass of the unit is given. It is 35 kg. Is to be supported on 3 springs in parallel, having stiffness of the each spring equal to K. Now see, when you are whether you are calculating omega n is root K by M, but now instead of K, we'll use Ke equivalent stiffness. Reason? Because now more than one spring is attached, and whenever more than one spring is coming, now whether you are calculating omega n, whether you are calculating zeta, formula to calculate zeta is C upon 2 root over Km. It is for general case, or C upon 2m omega n. But in that formula, at the place where K is coming, now instead of that, we'll take Ke, which is equivalent stiffness. So here instead of K, we'll take Ke. Ke is equivalent stiffness. So right now 3 springs are attached in parallel, and stiffness of each spring is K. So what will be equivalent stiffness? If spring are arranged in parallel, then in that case, to calculate equivalent stiffness, we add the stiffness of each spring. So if I will add the stiffness of each spring, which is equal to K, so equivalent stiffness will get which is equal to 3K. Now whether you are using the formula of zeta, whether you are using the formula of omega n, but in that formula, instead of K, K equivalent will come, which is equal to 3K. Good. So see, this refrigerator unit is supported by 3 springs which are in parallel, where stiffness of each spring is K, so K will be 3K. Now the unit operates at 480 RPM. So capital N is given, speed of the system 480 RPM. So we can calculate forcing frequency, that is omega. Omega will be speed of the system in radian per second. It will be 2 pi into speed in RPM, which is 480 divided by 60. And whatever speed of the system is coming in radian per second, that is nothing but forcing frequency. How much it is coming? 2 pi into 480 divided by 60. It is coming 50.2655 radian per second. Omega is given. Na? Now, only the 10% of the shaking force or unbalanced force is allowed to be transmitted to the supporting structure. So can I say the FT, force transmitted, is 10% of F naught, means 0.1 times of F naught, because more than that we cannot allow force transmission. It is given in the question. So indirectly the value of Ft by F naught is given, means transmissibility is given. So in this question, transmissibility is given. So in this question we have to find some other unknown, because transmissibility is already given. It is 0.1, and the value of transmissibility is less than 1, means it is 100% sure. If transmissibility is less than 1, means whatever value of R will come, it will be more than root 2. because for r is more than root 2, then only epsilon will be less than 1. But that in numerical, that automatically will come. Okay, that conclusion will automatically follow. Okay, so you have to calculate the stiffness is allowed to be supporting structure, then the value of k. K means stiffness of each spring. Exam asking Newton parameter. So here we have to calculate k. So firstly, from equation of epsilon, we will calculate k. After calculating k, we can calculate k also. But see, here you can see, see epsilon is given, good. But formula to calculate epsilon is square root of 1 plus 2 zeta r whole square upon square root of 1 minus r square whole square plus 2 zeta r whole square. It is good, here epsilon is given. But you can see in RHS 2 unknown is coming, na, zeta and r. Because right now equivalent stiffness is not given, it is unknown. That is our objective. Means omega n is not given. So if omega n is not known, r is also unknown, because r is omega by omega n, in which omega is known but omega n is unknown. So here indirectly r is known, and from since epsilon is given, from this equation we have to find the value of r. And after calculating r, since omega is given, we can calculate omega n. After calculating omega n, we can calculate k, and after calculating k, we can calculate k. But we will say, sir, here apart from r, zeta is also unknown. So from one equation, how can we can calculate two unknown r and zeta, because zeta is also known, na? Formula to calculate zeta is c upon 2 root over km, or k, not km, c upon 2 root over k equivalent into m, or c upon 2m omega n. No, here zeta is not unknown. Read the question carefully. See what this question is saying. The refrigeration unit is of mass 35 kg is supported on 3 spring in parallel, in which stiffness of each spring is k. But here examiner is not saying it is supported on 3 spring in parallel and a damper. Damper word is not used here, and in no places in the question damping coefficient is given. So right now this mass is only supported by spring, there is no damper, no damper. And since there is no damper, means can I say here the value of c is 0, and if c is 0, zeta is also 0. Yes. So right now since no damper is attached, so here zeta is 0, so value of zeta is 0. Okay, so now first I am simplifying this equation by putting zeta equal to 0. So put zeta equal to 0, this will be 0, so above said root 1 will be 1 upon square root of this part is 0, so it will be square root of 1 minus r square whole square. Now here epsilon is given, we have to calculate the value of r. Okay, just whenever na epsilon is given and you want to calculate the value of r, na, just write this equation like this: 1 upon, it will bring this outside root, na, it will be plus minus in bracket 1 minus r square. Okay, because if 1 minus r square is positive, then square root of this will be plus in bracket this. If it is negative, it will be minus in bracket this. If we are solving the numerical, just follow this. It will be plus minus in bracket 1 minus r square. Okay, epsilon is given. Epsilon is 0.1 is equal to 1 upon plus minus 1 minus r square. You will get the value of plus minus in bracket 1 minus r square, which is 1 upon 0.1, that is 10. So now first I am calculating the value of r by taking positive sign. So first take positive sign. Okay. Okay, and practical value of r, what is the practical value of r? R should be firstly positive because it is frequency ratio, it will be positive, and it should be real number. So r will always be positive and real number. So see, when I am take plus sign, it will be 1 minus r square equal to 10. It will be 1, bring 10 this side, so it will become minus 10, bring minus r square this side, it will become plus r square. So r square is coming minus 9. So that is not practical value, na, because if r square is minus 9, means here r is coming imaginary number, but r cannot be imaginary. So that is not a practical value. Na? So I am crossing, na, because it is not a practical value. Now calculate the value of r by taking minus sign. So it will be minus in bracket 1 minus r square, which is equal to 10. So it will be 1 minus r square. If shift this minus this side, it will become minus 10. Now bring minus 10 this side, so 1 plus 10. Bring this minus square this side, it will be plus r square. So r square is coming 11. So can I say r will be, if r square is equal to 4, na, r is plus minus 2, or means plus minus of square root of 4. Square root of 4 is 2. Similarly, if r square is equal to 11, na, r will be plus minus square root of 11. But r can never be negative, it is a ratio. So practical value of r is plus square root of 11. And plus square root of 11. Square root of 11 is 3.3166. And you can see what is the value of this r, na? It is more than root 2. Why? because on when r is more than root 2, only in that case we'll get epsilon which is lesser than 1, and right now epsilon is lesser than 1 because we have put the value of epsilon equal to 0.1. So whatever practical value of r I will get now, that will be more than root 2, but that is automatically coming. So we have calculated r. R is 3.3166. Now formula to calculate R is omega by omega n, which is 3.3166. So omega is known, so we can calculate natural undamped frequency. Omega is 50.2655 upon omega n, which is equal to 3.3166. So how much omega n is coming? 50.2655 divided by 3.3166. Is it coming 15.1557 radian per second? Now what is the formula to calculate omega n? Don't say root k by m and calculating k. No, here instead of k, k equivalent will come. Instead of k equivalent will come. So it will be square root of k equivalent by m, which is 15.155. So from this you can calculate k equivalent, and k equivalent is equal to 3k, so you can calculate k also. Or if you want directly replace k equivalent by 3k, so you can calculate directly k also. So first I am calculating, suppose k equivalent, so it will be square root of k equivalent upon m is the mass, and mass value is 35 kg, equal to 15.1557 radian per second. 15.1557 radian per second. So from this we can calculate k equivalent. It will be 15.1557 square into 35. So k equivalent is coming 8039.333 Newton per meter. Since I am using SI unit, so stiffness will come in Newton per meter, but it is equivalent stiffness Ke, which is nothing but 3K. So 3K equal to 8039.333 Newton per meter. So from this I can calculate stiffness of each spring, that is K. How much it is coming? It is coming 2679.778 Newton per meter. You can check calculation na. Yes. Now it is coming in Newton per meter, but examiner asking stiffness in Newton per mm na. So K will be, see, 2679.778. Now above side already Newton is coming. Now below side meter, and 1 meter is 1000 mm. So to convert meter in mm, in below side will multiply 1000. So this will be the value in Newton per mm. How much it is coming? 2.679 Newton per mm. So stiffness of each spring in Newton per mm is coming 2.679. Examiner asking in Newton per mm, so correct answer is 2.679, or you can also say 2.68. Clear? So this is the correct answer for this question. See, embarrass in GATE Aerospace na regard from entire structure section, in which strength of material subject will also come, vibration will also come. Nearly the weight is 20 marks. You cannot tell exact weightage, but approximate weightage you can tell. And out of this 20 marks, 6 to 8 marks, it might be possible sometime 9 mark question is coming. You can expect in GATE examination. Okay, Ambrish. So that's all for today. Today I have covered the vibration isolation part, and if any question is coming related to this topic, that is transmissibility ratio, I think you will be able to solve the problem. Clear? Similarly, in next week some other subject will start. Okay, and as approved sir is told in last session, that if you want that any specific topic we should discuss in the YouTube, you can mention in the chat box or comment section. Okay, if possible, the management team will 100% try to schedule the class of that particular topic if practically it is possible. Okay, apart from that, if any student is preparing for GATE 2027, they can join the proper batch of GATE Aerospace from okay, because we are launching proper batch for GATE 2027 for GATE Aerospace. Okay, but that's all for today class. Today we have completed the vibration isolation. I think it should be clear to everyone. I'm ending the class now.